Oh, I didn't have my mic, that's why. I was running out of time. Hello? Hello? Yeah, all of you sound happy. So, happy. Alina alternatif, Nina awatan, Kali Batama, Arabin Shankar, Colin Brown, Yuan Chen, David Crawford, David Wonky, Carl Allen, The Dongbu, WB, Thomas Canal, Kickoff Lecture, using me, Jeffrey Marquis Sanchez, Mira Aranova, Logan Allen, 1992, Poppy, Ryan Schneider, Ukun Pan, Brandon Christopher, Fall2021 Okay, let's get started then. Today we're going to talk about circuit theory, something that you should have been familiar with from your undergraduate courses. It is a pretty important theory because without circuit theory, we wouldn't have a lot of new technologies that we are enjoying now, like computers and so on. But circuit theory can be thought of as a subset of electromagnetic theory, as you shall see. Okay. How many of you have not had circuit theory before? All of you have had circuit theory, and all of you are bona fide electrical engineers. Okay. So as you can see, if you look inside the computer, basically, you see that all these components is equal to smaller. We engineer these components and we can take it but circuit theory plays a very important role, and you find that it's actually a part of electromagnetic theory. So the first circuit theory law that comes to your mind is the Kickoff Current Law. How does it come about? Well, you can say that it comes about because of Ampere's law. Ampere's law and the static limit. And if you were to take the divergence of this equation, okay, you were to take the divergence of this equation, you get 0 on the left-hand side, you have divergence of J on the right-hand side, and divergence of J essentially says that current is conserved. So if you have current flowing into a junction like this, if you were to apply this to a surface S that connects all these wires together, you find that the divergence integral, the divergence function can be converted into a surface integral, and then you have the surface of the volume. And so you can apply this, and then it will become like J dot NDS over a closed surface. And each of these integrals can be taken over only the section where the wire is flowing. And then you have Kickoff Current Law, which is like I have to disconnect somewhere. And let me make sure that I didn't miss anything. So you essentially have I1 plus I2 plus I3, IN have to add up to 0, which is the statement of Kickoff Current Law. And of course, we can say that some approximation is being made here. The approximation is that we assume no charge accumulation at the junction. You have learned that charge conservation is actually described by the current continuity equation, which is 0 dT, and then this would become minus J omega rho in the frequency domain. This was the precursor to Kickoff Current Law, which is this equation over here. And if we had had charge accumulation at the junction, then Kickoff Current Law would not hold true. But we are assuming that the charge accumulation is so little and the frequency so low that we can assume that this is essentially 0. And then we have Kickoff Current Law. So Kickoff Current Law goes through when there's no charge accumulation in the junction. And then we have Kickoff Voltage Law. How does this come about? Well, you can say that Kickoff Voltage Law comes about from Faraday's law. When the frequency tends to 0, or if we go to the static limit, then divergence of E equal to 0. Or curl of E equal to 0, sorry. And because curl of E equal to 0, we can define E to be the gradient of a potential by using potential theory. Okay. And because E is defined as such, then you can actually define a voltage drop between 2 points. Because when something is defined to be the gradient of something, you can actually perform this integration in closed form. Because E is an exact derivative, so this actually can be integrated. And you can show that if you were to integrate this between 2 points, it will be minus gradient of C dot dl AB. And you might have difficulty integrating this equation over a curve, but you can always break the curve into concatenation of straight lines. Okay, this might be a curve that you want to integrate over. And breaking the curve into a concatenation of straight lines allows you to integrate each line segment into a curve. How do you do that? Well, you convert this line integral into a 1D integral. So if you want to integrate in this line segment, just like as we did for the definitions of curve and divergence, you can say that this is a local coordinate system that you can always set up quite easily. And then if you were to define the gradient of C in that local coordinate system, like if I use that local coordinate system, it will be just partial x of C. And then if you were to perform this integration in that local coordinate system, it will be just this one. A to B, so this is the point A and this is the point B. And this can be integrated in closed form. The C at x is to the B minus C at x is to the A. So integral with a gradient in it can easily perform in closed form. If you were to calculate the line integral with the line. Because of that, we can define the voltage between 2 points quite easily. And then if you have this law, okay, you end up with something that you have learned in your undergraduate course, which is because of this, when you were an undergraduate, you can integrate this over a closed loop. And this has to be 0. And what it says is that if I have a closed loop, and if you don't like the concept of closed loop, you can always divide into concatenation of line segments, and then define the voltage from point A to point B. And you end up with the fact that the voltage V, VI, I to the 1 to n around a closed loop is always equal to 0. And this is what we have learned in an undergraduate circuit course as the Kickoff Voltage Law. So you can see that Kickoff Current Law is a consequence of Henry's law. Kickoff Voltage Law is a consequence of Faraday's law. Then remember, are there any questions before we move on? So, since circuit theory is something close to your heart, since all of you are electrical engineers, the picture we showed before, you say that if you have a closed loop, we can apply Kickoff Voltage Law to this closed loop. But if one of the elements is the source, like that, then we can actually replace that element with the next resistor. And if you take the voltage around and look for power conservation, you'll find that the magnetic resistor will have electrical function in the opposite direction to the direction of current flow, whereas in the other element, the current and the electrical function in the same direction. And we studied function theorem before. All the other elements are dissipated, but the element with the negative resistor is not dissipated, but it is actually the flow. So So some elements are important, and then you can apply Kickoff Voltage Law to this thing. And let's apply Kickoff Voltage Law and Kickoff Current Law, or maybe primarily Kickoff Voltage Law, to a circuit that looks like this. Okay, so it has a combination of resistor and inductor and the voltage source. So what we can do is actually to think of that this loop can be quite large, and I can apply Faraday's law to this loop. And in the beginning, I may not be correct to say that the right-hand side of Faraday's law is 0. Okay, so if you have this Faraday's law, you convert it into line integral on the left-hand side using Stokes' theorem. And then the right-hand side can be written as minus d dt of the flux linkage that this system has. Okay. And for most parts, and for most circuit theory, the right-hand side is small, because the d0 is small. For instance, this system will be 0. In the resistor, we have only electric field and electric current. In the capacitor, we only the auto primarily has electric field. In the inductor, we have but then magnetic field is local. So there may be a strong magnetic field here. And here is mainly electric field. You know that J is to the sigma E in the resistor, then inside it is mainly electric field. And you know that inside capacitor, as we have learned, you might have positive charges here, negative charges here, then I have drawn this few lines wrong. They're mainly electric field. So if you look at this circuit close up, B is essentially 0 inside this loop. Look, B is essentially 0 inside this loop, except for the B inside the inductor. You can see that the right hand side of this is essentially 0. Okay. So if you integrate the equation around the closed loop, A to B to C, and C to D, and then B to A, that closed loop to integrate to 0. Okay. So you think that if you integrate like this, sidestepping the inductor, we didn't go inside the inductor. Okay, we didn't go inside the inductor. And if this C is something like this, then it takes up no flux linkage as we integrate around this loop, and the right hand side is 0. Okay, everybody agree? So the right hand side of this equation is essentially 0 if I integrate from A to B to C to D. There's no flux. Magnetic flux is involved. Okay, so you can actually do this quite easily. You can show that voltage drop VAB. Okay, this must be equal to VBC plus VCB plus VBA. Okay. I should say that this is, maybe you can put a minus sign. Okay, I would have this this result. Some of the total voltage is still 0, and the voltage of the force will be equal if you flip the sign around, because it's VAB to VBA. This can be flipped to VBA. Okay. Voltage at the source is equal to the sum of the voltage mixed by the other. So this is what we learned in undergraduate circuit theory. But we have to take some care as to what actually happens around this inductor. Because we kind of gloss over it, we just integrate over here and claim that we will pick up a BCD as we integrate from here to here, but we never belabor as to what happens inside the inductor. So let's go into this inductor and take a closer look. If I were to integrate from C to D, what I have is that if I have current coming in and then current going out, I know that there would be a voltage drop across this inductor. Because of the voltage drop, there will be positive charges accumulating here. Because the voltage is not equal at the two terminals of this inductor. Because there are positive charges on the top end and negative charges on the bottom end, there would be electric field at the pointing vector. And this electric field is going to a voltage drop from the top terminal to the bottom terminal. So how do we find this voltage drop? Well, we can find this voltage drop by saying that if I use Faraday's law, okay, I would have the fact that the integration from C to D, which is E dot dl, okay, must be equal to integration from C to D, okay, must be equal to the time derivative of flux linkage D dot dl, dl, where S prime is this surface over here. Okay, that is what I should have. So you see that the flux linkage is going to give rise to what we call Lenz's law effect, giving rise to electromotive forces opposite to the applied electricity. And this allows us to relate the flux linkage on the right to the voltage drop across from C to D. So by so doing, then we can show that VCD, which is negative, actually is VBC, okay, and that should be equal to the time derivative of the flux linkage, which is essentially this one. Okay, that is the flux linkage. And this usually can be defined as L di dt. Flux linkage in an inductor is proportional to the current. The higher the current in an inductor, the more flux it will be generated. This is the property of an inductor. That proportionality constant of the inductor. So if we plug in the fact that the flux linkage is phi, we easily show that phi is linearly proportional to phi, and that proportionality constant is called inductor. And then we have the ideal relationship or the voltage current relationship of an inductor is given by that. Any questions so far? So we use an inductor to emphasize the right-hand side of Faraday's law. Okay, even though this inductor might be very small, and it's still very small compared to radius, you can apply this law at very low frequency field. Because even if the frequency is low or VDC is small, you still need the right-hand side support. So inductors are long elements used to amplify the right-hand side of the Faraday's law. And then we have another element that we use to amplify a part of Ampere's law that we have ignored. we say Kickoff Current Law follows from this. However, we have dropped this term. When we prove Kickoff Current Law, but displacement currents are sometimes important, and they can be amplified by using a capacitor. If you have a capacitor, then we show that because of the charges that go on both sides of the capacitor, there's a strong electric field. The parallel plate. And if you look at the displacement current, you think that two parallel plates is not small. It can be long. It can be long, but the capacitance is long. Because the capacitance is defined by Q equal to CV. The charge that you can pump into a capacitor is linearly proportional to the voltage that you apply. So if the capacitor is long, it means that you can pump in a lot of charges inside this parallel plate. It does not have to be parallel plate in two thin cords, which are very close to each other. And this device can be used to simplify the importance of this thing. So what I want to emphasize is that these elements are called long elements, and they actually bring out the importance of the displacement current in Ampere's law, and they bring out the importance of the flux linkage in Faraday's law. So when we have long elements in circuit theory, not everything in network equations is known. We still have displacement current, we still have flux linkage, we still have full Faraday's law. So circuit theory is wonderful. Even though it's an approximate theory, all the physics are there. The physics of flux linkage, physics of displacement current are there. You can do wonderful things with circuit theory if you know how. We haven't dropped any form in the circuit theory. In long term, the full market is a mix. The thing about it. And you can actually make many wonderful things out of circuit theory if you know how. So any questions on this? So this is just a picture of what happens inside the computer. This is the computer package, and you can see that well, the computer package is kind of sophisticated. You have the package, and you have the so the bottom one is called the package, where you connect signal from the outside into this chip, which is taking the sense of this package. And then the package for the chip now can have billions of transistors. Now the last and the right between them in the sense of billions of transistors. You have to send it to everyone. And they do it by what we call X-Fault line. X-Fault line is 3 line, many different levels. And the signal depends from the top. You can see on the right, there's a system called 4-gate array. 4-gate array are something on top of the chip. You send it into all the transistors, and then you can look at that. It will be a bit switches in the other options of 3-1. So these are 6 levels. And finally, the top is the transistor. But these things are on the order of non-equivalent. Because they are on the order, I guess, the smaller chip that we hear about is the type of non-equivalent.
You know what is the wavelength of blue light? If anybody knows, it's 450 in the morning to the dark. So this thing is much smaller than the wavelength of light. And when something is much smaller than the wavelength, we can use the electrostatic theory. We call it the nanoparticle, and that nanoparticle is very small compared to the wavelength. We need only to talk about classification. Now, inside this space, even though it's very complicated, you can just talk about that. Essentially, a scientific theory. Except for the case in the blunt element, the factors and stuff. Then have to show the effect of those things. You can get wonderful things out of this.
And I talk more about this in the lecture, but I'm not going to talk more about it. You can make decoupling capacitors, you can make spiral inductors, and you can make inductors on the chip. You can actually add them out of the spiral structure and so on. So if you don't have any questions, I'm going to move on to talk about transmission law. Okay.
Any questions before we move on to transmission? I presume that circuit theory is something that you read before as an undergraduate. So this is just a special course in circuit theory. But one reason is that circuit theory, in our opinion, is the substance of the relationship. Except for one thing, this object is consistent by different derivable from theory. So a large part of circuit theory is derivable. So if you don't say that to the circuit side, you get offended. Because the system bias. You have to go through some fault research. Yeah, that's a good question. The rule of thumb is that the smaller the better, which is not really useful, right? So, like I do a lot of computing, and we like to break things down to smaller pieces so that approximately basically stop. So, one thing of the wavelength is clear. So, in the lot, so in general, another way of thinking about that is that when you can defend yourself to a circuit theory, when you can defend yourself to a classical theory, the fact that people don't come up with
Great equation. We derived this equation before. We say Helmholtz equation is important for wave phenomenon. And then we also have Laplace's equation. So what it says is that when omega c goes to 0, then
Helmholtz equation can be approximated by Laplace's equation. What does this mean? Omega c tends to 0.
You can think about it. It means that the speed of light is infinite. There's one way to think about it.
The speed of light is infinite. It's also the same to saying that retardation effect becomes important. Retardation effect means that the delay.
And I think this is the same as Okay, another way of that CP. Let me see if I were to. So this is the same as omega C over, which is actually K, which is 2 pi over lambda, so omega C. And you have to compare this with something. Okay, this is dimensional. So it's useless to talk about dimensional quantities. So it's small. What is it small compared to? Okay, when we just make a statement like this is very big.
So we just say that this wave number is small.
To make it more quantitative, we will say that Ka is small. Okay, then you will have 2 pi A over lambda is small. So you have a ratio, which is the size
Of the particle, A is the size of the length compared to the wavelength you're talking about. If those two ratios are small, then we have it. Then in case if you're dealing with the particle like a nanoparticle, it's kind to fix for a light wave to travel. And nanoparticle is very thin. Then it's not a particle.
So just think of this. Any more questions? If not, I'd like to move on to transmission line theory, which is very important also.
You can think of transmission line theory as a four-man Maxwell equation. Maxwell equations that is too complicated. And you have to factor in and put the air out in the solve Maxwell equation. The engineers like to work with people. And transmission line theory is the answer to this very complicated theory. So how can we convert things to a multi-beam
Let's see how that happens. Well, transmission line theory can be used to describe a number of things as long as there are three parallel pieces of wire. You can use that to be a transmission line.
It can also be a power line. Power line is something that operates around 60 hertz. So the wavelength is small. And you still think of the power line complicated. Maybe computing portable. The wavelength is long, but the transmission line is more complicated. You have to include the propagation effect of propagation effect.
So how can we see propagation effect in transmission line? That will be the next topic. So you have transmission line has been just two pieces of metal. Okay, the symbol for the transmission line is usually given by that symbol in the Japanese. So transmission line is more complicated than this picture that is shown. And for instance, you can have a transmission line made of two input wires, just like this. And you can have it as a wave line. You can fix signals along it. And fix signals just like two parallel pieces of wire that you have in your dog. And this is a wonderful design in the sense that it reduces interference. I don't know if you can see this. You have 6 cross 2 wires. These are 2 parallel wires here. And it's shown the top here. Okay, I have what is known as crosstalk or interference effect. However, if this transmission line is in the presence of the magnetic field in the backside,
it could be something that comes from the power line. The power line is operating to low. Because it's very low frequency. And these are in the room that is You will see that that magnetic flux will have flux linkage to this crossing wire. In opposite polarity, some of the loops will get an positive flux linkage. The other loop will get this negative flux linkage. So on the average, the flux linkage is approximately the so the design like this picks up very little insecurity on the outside. It still comes up to the minimum. So we just use a very simple concept of Faraday to come up with this design. Then the mystery is that why is that we can transmit information? How does that happen? In order to understand that, we can start with the lump element picture. You can take any two pieces of wire and break it up into segments. Each segment can be approximated by an inductor, and then a capacitor in parallel in this manner. Why an inductor and why a capacitor? First, you have to understand the notion that if you have a piece of wire, you should flow a current I to this piece of wire. What is the first thing that comes to your mind if you flow current into a piece of wire? What is converted up in your mind? Anybody? What is present is true. But the other thing that the decision of this piece of wire is important to check the code. What things comes up so in your mind? When you check it, current into a piece of wire. Very good. We get it a magnetic field. We get it a magnetic field to ampere flow. Okay, so the first thing that comes to your mind is that a magnetic field is generated. So if a magnetic field is generated, it will give rise to stored energy in the magnetic field. Stored energy in the magnetic field is making it behave like a next topic device. Stored energy in the magnetic field are inductive. You can't tell it to inductor which is used to strong magnetic field. That magnetic field stored energy, and that is the inductor that is the so inductors can be used as approximate a piece of wire with a lot of current. So I have these two pieces of wire in parallel. Okay. And if you have two pieces of wire very close to each other, and if they are having opposite voltages, there will be charges accumulating on the top leaf and the bottom of the grid. And what do you see in your mind when that happens? Charges accumulating in the top leaf and charges accumulating in the bottom. What do you see? Very good. It's a constant, right? Electric field will now be generated. So the current is not going to be the only thing that happens in the transmission line. The current flow is different from the flow, but the current is not uniform. On this line, the current is not uniform. Divergence of J is not zero. There's another way of saying the current is not uniform. So the divergence of J is not zero. We expect Faraday. Why? And those charges are going to produce electric field. Okay, and when you see electric field, you immediately think of energy storage. Now the energy storage is in the electric field. And hence now we have a capacitor. So you can think of two pieces of wire, if you break into pieces, as consisting of inductors and capacitors in this manner. So this makes sense. Okay, these are modern states. So at least to make sense. No, I have two wires. I can never guarantee this. I just inject current into this two pieces of wire. I can never guarantee the current. It will only be a constant if, well, again, it goes back to the retardation effect. It will only be a constant if there's a few DC. If you inject current into this wire and put it back, you get the current into the wire, put it back. Okay. Because of retardation effect, that current is get the current in, you need to pull it out of it. Basic current. Okay. Pull it out of it. That current has no time to respond to the effect that pulling current in and out of it. So you do that. So the current is not usually something due to retardation effect. And then the current is not usually something with the fact of accumulation certain part of this water. So the proper way to model this two pieces of wire, the model is as a concatenation of the inductors and the transmission. This is called the long element model. So this makes sense to people. There's two more modelization.
So then this is something simple. All of you know how to analyze this thing. This simple circuit theory. So we write Kickoff Voltage Law in this loop, for instance, and then we can write Kickoff Current Law here. And all these are the same. It's just a replica of the same circuit over and over again. So we know how to write Kickoff Voltage Law and Kickoff Current Law here. It is the same for all the rest. The only thing is that the voltage is not a constant. Okay, the voltage is not a constant. So let's assume that they differ from each other by just a little bit called delta V. And then just a little bit by 2 delta V 2 times down the line. And the current is not going to be constant also. Okay, as we argued just now, the current is not going to be constant. So the current I flowing here, and then by Kickoff Current Law, this I should be that I. But because of the capacitance leakage, the capacitance coupling, the current is going to be different. Just some of it that leaked out. And you can write down Kickoff Current Law and Kickoff Voltage Law. And by so doing, actually, if you want, I can derive the equations for you, but if you understand the physics of it, it's more important to understand the math of it. Okay? So if you understand the physics of it, what we find is that, well, first you write down the ideal relationship of an inductor that all of you know by undergraduate knowledge. Okay, this is the ideal relationship of an inductor. But let's assume that this inductor is different. The inductor that we have is the line inductance times delta V, and this is called line inductance. Okay, this is inductance per unit length. So when we have that model, we give a line inductance, and we can figure out the inductance per unit length, and that's more inductance that we have over there. Okay, that's why we say this inductance is actually L delta G, the line inductance, and this is the line capacitance, and this is actually line capacitance times delta V. Okay, so if you work this out, then what you have is that you have L delta V, the I dt, okay, is equal to V minus V D plus delta V. So you take the voltage difference at 2 nodes. You take the voltage difference at these 2 nodes. Okay, which is these 2 nodes. And then relate it to the current that passes through the inductor. And this is the equation that you have. This is just simple circuit theory. And then you now assume that delta Z is going to 0. So this would now become something like let me see, how did I write it? It's minus delta V, delta V. Okay, the right hand side can be written as the distance in the voltage divided by delta V. Okay, did I write it? This delta V, sorry, this delta V. Incremental change in the voltage. Now, if I divide by delta V, I will get minus delta V over delta V. And in the limit, when delta becomes very small, this becomes, let me see what I use. I actually use a partial derivative here, because V can be a function of both V and T. Okay, and you can make I both a function of V and T as well. And then you have a partial differential equation, L partial I, which is a function of G and T, is equal to minus partial V, V of G of T. So you got this very nice equation. Looking almost like Maxwell's equation. It's a four-dimensional Maxwell's equation. If you compare it with the Maxwell's equation, that would be you will have this thing is minus curl of E. Okay, you have this as Maxwell's equation, but this is a four-dimensional Maxwell's equation. This one B. Okay. But having just Faraday's law is not good enough. You have to express something that looks like Enfield law. Out of it, something like theory, and you can do that by writing out the other equation. Okay, I wouldn't go through the circuit theory to do that. If you do that, then you would have, let me see, what would you have? Okay, so we get one equation already from circuit theory. And then the other equation, you can also use lump element and just use Kickoff Current Law instead of Kickoff Voltage Law with this second equation. Okay, I wouldn't derive the second equation as just assume that you can do it at home. Very similar to how we derive the first equation. You go and balance the voltage and the current. Apply Kickoff Current Law. Okay, one of these notes, and then you can actually arrive at this equation by taking the limit, and delta V becomes very small. Okay. So the second equation now looks like, if the first equation looks like Faraday's law, what does the second equation look like? Ampere's law without the term. Ampere's law with only the displacement term. So this is wonderful. Maxwell's equations become so simple. And then what we can do is that we can convert this into a wave equation, just like what we did for Maxwell's equation. We have two Maxwell's equations that are too complicated, so we bind them into one. We can combine them into one by, say, taking the derivative of one of these equations. I don't know, you might choose to do it differently from me. Okay, so if you just differentiate this with respect to times 2 times, then you have partial V, partial PV, right? And then you can use the second equation to eliminate partial PV. And then you should end up with the equation that I hope I didn't make any mistake. Why don't I just multiply this equation with C? So I've got a C here. And then I will have partial V square R. Okay, can you see that? So I combine the two equations. I have this equation, and this equation is familiar to all of you. And you have studied it before. What is meaning we call this equation? Second derivative in time, second derivative in space. This one dimensional. Very good. Wave equation actually is the wave equation that we studied earlier in the course. That if I write it in a more familiar form, maybe you will see it. Okay, you can do the same thing, eliminate I from the two equations, you get okay, you get these two equations, a two-wave equation. One wave equation is for the current, the other one for the voltage. So by simplifying things, you can see waves to knock out from this very simple transmission line theory. These are called the telegraphic equations. They were actually derived by the telegraphers before Maxwell's equations came about. Okay, and they're very simple, and so if I were to ask you to identify the velocity of the wave in these two equations, what is that? You get very good memory very good. Okay, so this equation, if you put it and do a side-by-side comparison with the wave equations that we have. Okay, the wave equation is right in terms of velocity was this one. You immediately see that V is equal to 1 over square root of the alpha. Wonderful equation. And it comes about because you really never back out the long parameters and deriving the reducing the inductors, reducing the capacitors, and you said the displacement current from the model. Never before, and the substitute before. Never before. We come up with a very simple formula. Which is only found like Maxwell's equation. Okay. Any questions on this? So you know how to solve wave equations, and we can just talk about it a little bit. Okay, but there is a voltage and there is a current, both of which are based the same equation. So there is actually a relationship between the voltage and the current. They're not independent. As you can see, once you know the voltage, as we said before, okay, once you know the voltage, you know the current. Once you know the current, you know the voltage. They're coupled to each other, just Maxwell's equation. Once you know the E field, you know the H field. Once you know the H field, you know the E field. Okay? Which means that E and H are related by something called E, and free space, and are related by something a constant, something we call a constant for things. Remember what the constant is? Yes. Impedance, very good. Usually we call that intrinsic impedance of free space, which is small. 275. So with the recognition, all remember this. Impedance of free space, impedance of free space, 175. So because of this, since this is using the Maxwell's equation, there is also a relationship between U and R. In the topic,
that relationship is not called intrinsic impedance anymore. The I and DC are not related. The relationship is called this characteristic impedance of the transmission. Okay. I think most of you have had transmission line theory before, am I right? All of you who have no transmission line theory before. You don't have. Okay, you don't have. But so far, I think you can follow it. Very similar to wave theory. Except for the topic. And here's the part where it departs from the wave theory. Instead of having a relationship between E and A, we have a relationship between I and B.
And that relationship is the characteristic impedance. Okay. So if you have a transmission line, if you have a wave traveling on this transmission line, by the same token, there is also a wave that you can describe in terms of current traveling on this transmission line.
Those two waves are related to each other. And if you have one wave traveling in one direction in terms of B, there's also a corresponding time that travels with it. And you travel in the same direction. And if you're traveling in the same direction with the
Plane wave in free space, then what you have is that this ratio, I'm not going to derive it, it's derived in the lecture note. Then if you have no transmission line theory before, this ratio is L over C. And for vector mnemonic, you will remember that for plane wave, that ratio is mu naught over epsilon naught. So this is something that has
the unit of Henry's transmission. And what mu naught is the line, is the thing of Henry's transmission. So it's called the transmission. So it's something like that in terms of the unit length. And epsilon has the unit of direct transmission.
okay. And it turns out that this thing now, since it's a line inductance,
it also has a unit of Henry's transmission. Here also has the unit of direct transmission. So the units are the same.
and both of them have the units of impedance. This is the intrinsic impedance, this is the characteristic impedance. Okay, so this have the units of ohm, or Siemens now. Nobody calls ohms anymore. Okay. So I'm not going to derive this formula, but it's derived in the lecture note.
Something that is kind of stupid, that if you have a voltage on the transmission line, you have to be related to the current by the constant that comes to its characteristic.
So what is more interesting? Any questions on this before we move on? Okay. So what is more interesting is that what happens if you have
A more general structure, rather than the simple one that we have shown you. There's no law. We have only inductance and capacitance in the transmission line. What happens is the transmission line has stopped. We will have to model the transmission line with some resistance somewhere.
And so if I start out with this transmission line theory that I had before, okay, I had the one with no loss. I draw this simple picture. And we derive wonderful graphic equation from it.
Very simple model. But that was not enough, not good enough for many applications. The real world is not devoid of loss. We always have something that belongs. And you connect two pieces of wire. That wire is not a perfect inductor. And then when you put two pieces of wire together, it's not a pure capacitor. It's something you put the charges that also inductors together. what are the uses in the capacity. We have current between the capacity with the resistive loss in a piece of wire. So it will be more appropriate to think that when we have resistive loss in a piece of wire, okay, that wire is not just an inductor, but it will be something in series with a resistor. Okay, and then when we have a capacitor, then if we have some loss, if two pieces of metal make a capacitor, but that capacitor is something that has a leakage. Okay, it has a leakage that looks like this, so you can model it in this shunt resistor. The shunt resistor is the series resistor to model the loss. So a proper model for a transmission line that is more general than what we have just learned will be something looking more like this. So you know what I mean. You just have to put a resistor parallel to this one. The resistor in parallel to the capacitor accounts for leakage loss in the capacitor, and then the resistor in series with the inductor accounts for copper loss in the piece of wire that connected to the inductor. We have this process. So this is a problem more complicated to solve. But we are doing the recipe and now. So what method would we use to solve this problem? Very good. This favorite. Whenever you see the active element in the proof of theory, you use favorite. That you have done in the undergraduate course. When you see induction, capacity, resistance, equations are very complicated. However, we use favorite technique and looking at frequency. Equations are greatly simplified. And then you would replace it with something that is more like a Z or Y, a Z, and then a Y. Okay, you see what I mean? I don't draw very well, but you see what I mean. So those Z's are all identical to each other, those Y's are all identical to each other, but they have elements that account for loss in the system. So what are the equations that we should be worrying about? Then we know that in the time domain, in the first one, we have dV dz is minus dt I Li. Let me see. Before that, we have this equation. This was the Kickoff equation, one of them without loss. And now if we want to repeat this equation for velocity line, so we can rewrite this equation as K omega Li in the frequency domain. Okay. So you notice that K omega L is just the series induction of the wire. Okay. So I can think of this as minus Di. And then I can choose the Z to be a different type now. If I want to, I can generalize this to J omega L plus R I, and that will be my Z. So I have easily included loss in one of my two Kickoff equations. Okay. But the same token, the other Kickoff equation that I have, which was the I, the Z is minus, before that it was just C, the C, the V, right? And then I can convert this into minus J omega C V. Okay. And again, I can convert this back into something quite easily in the frequency domain, that the IDZ is J omega C plus C. If I want to put in the shunt resistor now, you see that the second derivative equation accounting for the shunt resistor is just this. Or I can write it more suggestively as minus YB. Okay, so this is one of my equations. The other one is dV dZ minus VI. So two equations, two unknowns. It's very much like writing Maxwell's equation for a lossy thing. But anyway, a Kaiser technique that makes it a piece of cake, right? You just replace whatever incidences that they simply agree with a complex number. You take V as 1. Do you know how to solve these two equations? Do you know how to eliminate one of the two unknowns from them? We've done that for lossy Maxwell equation before. So what do I do to eliminate I or B from the and how do you right. Very good. If differentiate one of the two one more time with the B, and then you can substitute the second equation. So you have this lossy Helmholtz equation. Okay. Lossy Helmholtz equation. Sorry, this is the I, and then this is the B. Okay. I do have these two equations, but we are no more different than the Helmholtz equations that we've seen before. So we've seen Helmholtz very different. I just want to be able to say. Okay, so this is just how to you know how to stop. You contract that for you one enough. So are there any questions? I guess I shouldn't move on, because if I move on, it will be going to the next topic, which is what happens if you terminate this transmission line? Okay, what happens when you terminate this transmission line? So if you have this transmission line, schematically you can make them look like this. What happens if you terminate with the load incident? Okay, we'll talk about that next time. So for reflection from this transmission line, when you have a load that's fine, so what happens when the power line comes the power to your head? So you have to refrigerator, you have the washing machine, you have all kinds of machines at home. Okay, I'll stop here.
I'm gonna be a little late to class.
Okay. Okay, thanks for coming. Thanks for coming. Thanks for coming. Bye-bye. Okay, thanks for coming.